All right, so let's look at number 6. All right, so for number 6, they asked us, given the derivative, so if you'll notice, this is already the derivative of g of x. So given this derivative, where does the derivative exist? So the derivative is going to exist for the values that are in its domain. Remember, your domain is going to be all real numbers unless one of two things happens. You have 0 in the denominator, or you have a negative under an even indexed radical. So when we have a denominator, we're going to say that our denominator cannot equal 0, so x cannot equal 3. And we're going to say what's underneath the even indexed radical has to be greater than or equal to 0 since it can't be negative. So x is going to be greater than or equal to negative 1. So to give that an interval notation, we're going to start at negative 1, and we're going to go from negative 1 to infinity, but we're going to have to leave out 3. So we're going to go from negative 1 to 3, stop there and jump over the 3, and then go to infinity. We can equal the negative 1, so bracket there. We cannot equal the 3, so parentheses there, and always a parenthesis with infinity. All right, then for number 7, it gives us a piecewise defined function, and the clue here is show that the function is differentiable at x is equal to 2. So to begin with, I'm going to figure out what my derivative is for each of these pieces. So when x is greater than or equal to 2, I've got x cubed minus 5x, so the derivative of that would be 3x squared minus 5 when x is greater than or equal to 2. And when x is less than 2, my function is 2x squared plus 3x, so the derivative of that would be 4x plus 3. So they ask me, is it differentiable at 2? So to check that, I'm going to take the derivative from the left at 2 and compare it to the derivative from the right at 2. So the derivative from the left is this guy right here, and the derivative from the right is this guy here. So if I'm checking at 2, I'm going to plug 2 in, and I get 11. Whereas from the right, I plug 2 in and I get 7. So since the derivative from the left at 2 did not equal the derivative from the right at 2, then it is not differentiable at 2. You could not just say it's not differentiable at 2. You have to show work to support that for why that would be true. You also cannot say that the derivative from the left is not equal to the derivative from the right, because there is going to be a place where 4x plus 3 is equal to 3x squared minus 5. So there is a place they'll be equal. I need to specify that they're not equal at 2. If I had gotten the same value here and here, like I had gotten 11 equals 11, then I would say that it is differentiable at 2. All right, then for number 8, they ask us to find the derivative of a product. And I worked this one out both ways. I worked it out where we did first times derivative of second plus second times derivative of first. And then I worked it out where we simplified first before we took the derivative. And you can see this is definitely the easier way. So we've been talking about simplifying first before you take a derivative, if at all possible. So up here, if we did first times derivative of second, we would do derivative of x cubed plus 2x squared minus 4x. That's what you see right here. Plus second times derivative of first, that's the derivative of x squared plus 6x plus 5. The problem is then I have to go through and multiply x squared times each of these, and 6x times each of these, and 5 times each of these. That's what you've got all right here. And then I've got to go through and take x cubed times each of these, and 2x squared times each of these, and negative 4x times each of these. That's what you've got all down here. And then combine all my like terms. You can see that it would be much simpler to go through and multiply here. So x squared times each of these, 6x times each of these, 5 times each of these is how we got this line. Then we combine the like terms, and then we only have to take the derivative of this one string right here using power rules. So the derivative of x to the 5th is 5x to the 4th. Derivative of 8x to the 4th, we're going to do 4 times 8 is 32, and then reduce that by 1. Derivative here, 3 times 13 is 39, and reduce the 3 by 1. And then 2 times negative 14 is negative 28, reduce the 2 by 1. And then the derivative of 20x would just be negative 20. So you can see we're going to get the same answer either way. It's just definitely easier the second method, but your choice, whichever one you want to use. All right, for number 9, we don't have a choice. There is no way to simplify that algebraically, so I am going to have to use quotient rule. I'm going to have to do denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. So denominator derivative of 3x squared would be 6x minus numerator derivative of denominator 3 times 2 would be 6x squared minus 5. And then again, denominator squared. So I'm going to simplify up here. So I'm going to do 2x cubed times 6x and negative 5x times 6x. And then here 3x squared times 6x squared is going to give us 18x to the 4th. So it would be minus that 18x to the 4th. And then 3x squared times negative 5 would be negative 15x squared, and it's minus that negative 15. So minus a negative would be plus 15x squared. So we could combine the 12x to the 4th minus 18x to the 4th to get negative 6x to the 4th, and then negative 30x squared plus 15x squared is negative 15x squared. You could take a common factor out of this, but it won't cancel top and bottom, so there's no need to take it out. But you could if you wanted to leave your numerator in a factored form, just like your denominator. You also do not need to FOIL this out. You can leave it in its factored form. All right, then number 10 dealt with particle motion, and they gave us our equation t cubed minus 27t. And first off, we want velocity, which is the first derivative. So the derivative of t cubed is 3t squared. Derivative of negative 27t is negative 27. Then acceleration is the second derivative. So we're going to take the derivative of velocity. So that would give us 6t plus 0. And then jerk is the third derivative, so we're going to take the derivative of acceleration, so the derivative of 6t would be 6. Then they wanted the velocity at 2, so we can come back and we can take our velocity equation and plug in 2 for t, so 2 squared is 4 times 3 is 12, and then 12 minus 27 gives us negative 15. To figure out where this is moving forward, moving backward, and at rest, all of that comes from velocity. So I'm going to need to take my velocity equation, 3t squared minus 27, and set it equal to 0 and solve it. So I'm going to add 27 to both sides, divide both sides by 3, insert the square root on both sides. Don't forget to put in your plus or minus, and you'll get plus or minus 3. So for velocity, I have an x-intercept at positive 3 and at negative 3. So anywhere that velocity is equal to 0 is where my particle is at rest. So it's going to be at rest at 3 and negative 3. Then it's moving forward where velocity is positive and backwards where velocity is negative. So I need to figure out where this is positive and negative. And the way that I do that is with a test point. I'm going to pick a point that is not an x-intercept. So 0 is an easy point to pick if it's not an x-intercept. Since this is the sign graph for velocity, I'm plugging that test point of 0 into my velocity equation. So if I come up here, this is my velocity equation, and I plug in 0, I'm going to get negative 27. So it's negative at 0. When we cross over a single root, the sign changes once. And when we cross over a single root, the sign changes once. If you would rather test each of these intervals, you can do that as well. So now we know that from negative infinity to negative 3, this was positive, so moving forward. From negative 3 to positive 3, it was negative, so moving backwards. And then from positive 3 to infinity, it was positive, so moving forward. Then the last thing we want to know is where it is speeding up and slowing down. And so for that, I'm also going to need a graph of acceleration. So let's take our acceleration, which was 6t, and let's set it equal to 0. And so divide both sides by 6, we'll get t equals 0. So I'm going to label this for acceleration. I've got an x-intercept at 0. So I can't use 0 as a test point because it's an x-intercept. So I'm just going to come over here and use any value over here on this side. I'm going to use a positive 1. So if I take positive 1, and again, this is the sign graph for acceleration. If I'm trying to figure out where acceleration is positive and negative, I plug it back into the acceleration equation. So I'm going to test positive 1 in the acceleration equation. That gives me a positive 6. Cross a single root, the sign changes, or you could have plugged in a negative 1 and you would get negative 6. Now, so that's a little bit easier for us to compare the velocity to the acceleration. I'm going to add a few things on here. So you can see that this is still positive over here and negative all in here. I just added an extra little negative sign here just to make it easier to compare, and still positive over here. We said that acceleration was negative all over here and positive all over here. So again, all I've done is just added a few signs just to make it a little bit easier to compare. All right, so you can see that if we look at this first piece from negative infinity to -3, you can see velocity is positive and acceleration is negative. So they're different, so it's going to be slowing down there. Then if we compare from -3 to 0, you can see they're both negative there, so it's going to be speeding up there. If you compare from 0 to 3, you can see the signs are different there, so it's going to be slowing down. And then from 3 to infinity, the signs are the same, so it's going to be speeding up. So that's how we can compare those two graphs. All right, then for number 11, remember that anytime you see the word marginal, that just means derivative. So they gave me a cost equation and they asked me to find the marginal cost. So all I need to do is just take the derivative of that. So the derivative of a constant is 0. Derivative of -6x cubed would be -18x squared. And then derivative of 5x to the 5th, 5 times 5 is 25. Reduce this by 1, 25x to the 4th. All right, then for number 12. They told us the figure depicted the path of a baseball, and they wanted the instantaneous rate of change when the distance from home plate was at x is equal to 60. So basically, we want to know the instantaneous rate of change at this point right here. Instantaneous rate of change is derivative, and derivative is slope of the tangent line. So if I can hand draw a tangent line right there at x is equal to 60, then if I can find the slope of this tangent line, that'll be the same as the instantaneous rate of change. So I just picked 2 points off of my line. That kind of looked like 50-25 to me, and it looked like 70-15 to me. So I just used my slope formula, y2 minus y1 over x2 minus x1, and that gave me a -1/2. You also could just look at it and approximate, like, your rise over run, like it looks like it's running about twice as much as it's rising, and so you might approximate a -1/2 that way as well. It is just an approximation. It doesn't have to be perfect, so don't worry if yours is a little bit different than mine or yours is off a little bit. All right, then for number 13, they ask us to find the derivative of our trig functions. And so we know that the derivative of secant is secant tangent. The derivative of cotangent is negative cosecant squared. So minus a negative gave us plus 3 cosecant squared. And the derivative of tangent is secant squared. So just utilizing those trig formulas there. All right, 14, we have first and second derivative. So for our first derivative, we're going to need to use our product rule. So we're going to say first times derivative of second, derivative of sine is cosine, plus second times derivative of first, derivative of x squared is 2x. So that gave us x squared cosine x and then 2x sine x. So there's our first derivative. So to find our second derivative, we're taking the derivative of this. So let's start with this first piece right here. So we're going to need to use product rule for this. So I'm going to do first times derivative of second plus second times derivative of first. So first, x squared times derivative of cosine is negative sine, plus second cosine times derivative of first, derivative of x squared is 2x. So this whole thing right here is product rule for this piece. All right, now we need to do product rule for this piece. So again, we're going to do first times derivative of second plus second times derivative of first. All right, so to clean this up a little bit, we've got negative x squared sine x, 2x cosine x, 2x cosine x, and 2 sine x. So we can combine the 2x cosine x and the 2x cosine x to get 4x cosine x. All right, then for 15 and 16, for these two, we want to simplify these problems before we try to take the derivative. It will make our life so much easier. So we know that tangent is sine over cosine. If we cancel these cosines, then we're just taking the derivative of 5 sine x. The derivative of sine is cosine, and I'm done with that problem, as opposed to having to do first times derivative of second plus second times derivative of first.